Unmute, start video. Let me put my little thing on.
Why didn't we have any like blanks to fill out this week?
Well, we are just barely touching on chemistry here at the end of the year. And with that being the case, we're just going to breeze through it. So your lessons are going to get a little shorter.
The labs from lesson 29 or lesson 30. Oh yeah, lesson 30 is all about the Rube Goldberg.
Yes, they're going to become nothing but Rube Goldberg. You are correct.
Oh, Miss Danny, I don't think I'm gonna be here next. I have tech.
Next week, you have tech week? Okay.
Bauer.
Yes, it is. Where's the junior one? It's that one. There it is.
Yes.
Adams. It said there's supposed to be.
Did you figure out whatever you were looking at?
Yeah.
You good? Okay. Good morning. What's up? Missing your brother. There he comes. Dump, dump. Good morning. Did everybody have a nice break?
Yeah.
Did everybody get to see some bit of the eclipse?
Yeah.
Yeah?
I did the total.
Where'd you go? You went all the way to Ohio and back? And you made it?
We kind of made it into a road trip, so we went
Mhm.
first to Pigeon Forge.
Oh, I love Pigeon
Then
Forge.
to Kentucky.
Mhm.
And we went to Chicago.
Was the traffic bad leaving and getting in?
Yeah.
The 2017 eclipse, we went up to Toccoa, but Jason's parents and his sister and our niece and nephew came down from Virginia. And then we all went up to Toccoa together and they got stuck. It took them 6 hours to get from Toccoa to I-85, which is not very far. So they got very, very stuck because the traffic was so terrible.
We
But
literally got home like at 1 o'clock this week.
wow.
AM?
Yeah, it must have been AM. Now Cole's in Waco and Waco was in totality. And we were worried he was gonna have
It was so cool.
too many clouds, but it was cool. So yeah, I definitely recommend to everybody, if you can get a solar eclipse in totality in your lifetime, do it. Yeah, there's gonna be one in 20 years in Florida, I think, 20 some odd years, but it's gonna be in Florida and that, that's gonna be crazy because everybody's gonna flock in and there's only one way, like 1 or 2 ways in and out because it's a peninsula. So that's gonna be madness, but hey.
Yeah, 2 major highways to get out. Did you travel for?
I did not. I watched the 85% we got here with our glasses, but Cole, we got some pictures out of Waco and Cole got to see it in totality twice, but we saw totality in 2017. So that was amazing. Like amazing. All right.
5% here in Georgia.
Yeah, we had like 84.75 or
Yeah, it
something.
was pretty close to
Yeah.
totality in Georgia last time.
Yeah, we did too. All right, so we are moving on with chemistry a little bit. And so Eunice was asking, why are the lessons so short and there's not as much to write? And I said, well, they're just going to get that way these next couple weeks. They're just going to be your next, like, yeah, we're just touching on it real lightly so that we're warmed up for next year. And for those of you who won't be here next year, you're at least kind of familiar with it anyway, because you'll do it at some point. All right, there is a Mentimeter today if you have your phone. If not, we'll just do without the phones. So here we go, inside of an atom, dum, da, da, dum. All right, so we have different subatomic particles, right? We've got protons, electrons, and neutrons, and these are our subatomic particles. So which ones are positively charged? Alrighty, Eunice. Those are protons. They are positively charged subatomic particles, and they're found in the nucleus. Now, what are the negatively charged ones, Emma? Electrons, yes, those are negatively charged subatomic particles, and they're found in the space outside the nucleus. And Nico, what else have we got? She did electrons. Protons, electrons, neutrons. All right, there they are. So they're neutral. Now, I kind of made these colors of the font as close as I could to the colors in the model. So you can kind of see where you could expect to find those particles. All right, so protons, neutrons, and electrons can be distinguished in a couple ways. How do we distinguish them? Do you know? Do you know, Eunice? Are you looking? I'll tell y'all. So we can distinguish them by mass, charge, and location. So we just talked about charge and location. Now let's talk about mass, charge, and location. So for our, what color were the green ones? Who remembers from the last graphic? Yep, see, there they are, protons. So does anybody know the mass of a proton, the charge of a proton, and where it's located? What do we know?
The protons are located in the middle
Yeah,
and they are positively charged.
yep. Do you know the mass might be? It's a tricky one. So for protons, we've got a mass of 1.67 times 10 to the negative 27 kilograms, or we call it 1 AMU. And yes, they're positively charged and they're found in the nucleus. Okay, AMU is atomic mass unit. It would be ridiculous if we tried to measure subatomic particles with kilograms, because look at what we get. 1.67 times 10 to the negative 27. What's 10 to the negative 27 mean?
10 times 10 to the negative power of 27.
Yeah, so is that a big number or a little number?
Big number.
Think about it.
Little.
Negative, so it's a really little number. So can you imagine in your head what that would be in kilograms? Like, you can't even conceive of that, right? Like, it's so small. 1.6 times 10 to the negative 27 kilograms. You can't even imagine what that is. So instead, we've come up with a new unit, and that's an AMU, or an atomic mass unit. So we say protons are 1 AMU, okay? All right, now, how about neutrons? Anybody know about what the mass of a neutron is or where it's located? Emma, you go again? Go for it.
Neutrons are located on the outside. They
Think we're good. Outside, or
they're located in the inside.
look at the picture. Neutrons are the blue ones, so they're
They're
in the nucleus. Okay. And what's the charge of them?
negative.
No, neutral. There you go. Neutrons are neutral. You got it. Electrons are the ones that are negative. Neutrons, neutral. You want to say N negative. That's an easy thing to do, is to go, oh, it starts with N, it's negative. But you want to think about the whole word, neutral. Okay, so here's what neutrons have for mass. Oh, what do you know? About the same, isn't it? So we also say they have 1 AMU. All right, so when we're looking on the periodic table, for example, helium is going to be an example I'm going to use. So helium right here, here's your 2. That tells you, that's your atomic number, and it tells you how many protons there are. But if you look at this little number here, this is your atomic mass, and it says 4.0026. This is in AMUs. So it's roughly 4 AMUs, which makes sense if each proton is about 1 AMU and each neutron is about 1 AMU. So you get that, and there's 2 protons and 2 neutrons. So that's 4, right? 2 protons is 2 AMUs. 2 neutrons is another 2 AMUs. So now you have 4, right?
Does that mean electrons weigh nothing?
Pretty much. We're about to see that. So here's what electrons
Also,
weigh.
I can't see.
Yeah, hard to see. So your electrons are 9.1 times 10 to the negative 31. So that first number is bigger. We had a 1.67, now we have a 9.1, but look at the exponent. Negative 31 is a whole lot smaller than negative 27, especially when you remember we're doing exponents, right? So exponents, that number multiplied times itself, but we're doing that negatively. So if you're picturing a number line, we're like way.
It's like 0
Wait,
and 31 zeros and 9.
Yeah, kind of. Yeah, kind of. So, but if you look at what they weigh, the mass that we give an electron is 0.000548 AMU. So basically, when we're trying to come up with the mass of an atom, we pretty much don't count the electrons because they're so small. We don't really count them. Okay. So when we look at masses on here, we tend to round as well, just so you know. So we round. Now, I want you to notice something. Helium is 2, which tells you it has 2 protons, right? And we said its mass is 4, so we know it has 2 protons, 2 neutrons. But hydrogen's number is 1. It has 1 proton. Well, but its mass is 1. So what does it not have?
It doesn't have neutron.
It doesn't have a neutron. We know it has a proton because its number is 1 and its mass is 1. So you would think it would be 2, right? You would think it'd have 1 proton, 1 neutron, but hydrogen doesn't even have a neutron. It's just like a proton and an electron. Yeah. So if you look here, we actually call it a diatomic nonmetal, and we kind of lump it in with these others. And we'll talk about this table and how it's organized a little bit more over the next couple weeks. So here's what we were just looking at. Now we're going to look at it a little more up close here. So atomic mass and atomic number. Atoms of different elements have different number of protons. So what is the number of protons in an element? What do we call that? What do we call it?
The atomic number.
The atomic number, right? And what is the atomic number of carbon? Can you tell by looking at it?
6.
6. There it is. Okay. And I've got it in the same color again, so you can see it. So here's carbon. 6. All right. And what's the sum of the protons and the neutrons? We just talked about it. What's that going to be? Well, when you add them up, what do we call it? When you add up the mass of the protons and the mass of the neutrons, we call it the, do you know?
Isn't it an atomic mass?
Atomic mass, or we also can call that mass number. Now, it says the sum of the protons and neutrons, which is really kind of the same thing as this, or almost the same thing as the mass of the protons and the neutrons, because it's 1, right? So if you have in carbon 6 protons and 6 neutrons, then you can just say 12 is going to be our mass number. And really what you're adding is not the number of subatomic particles, but the mass of those particles, which is why it's not just 12. That's why it's 12.0107, because there's a little difference. Neutrons are a little heavier really, but it's kind of negligible at this level of chemistry, at least. All right, so a chemical bond forms between 2 atoms when what is moving between them? What happens? Which of these particles are involved? Do you know? Electrons, yes. Okay. So specifically what we call valence electrons. All right, so we're going to be talking about this, and this is what we're doing in lab today. So electrons in an atom are not in the nucleus, right? Your protons and neutrons are in the nucleus, and then your electrons are moving all around the outside. And see, I've got them on my clothes today. Whoops. The electrons are moving all around the outside. Now, they're actually moving in shells. Have you ever had an everlasting gobstopper?
Ooh,
Where you suck on it and it's pink, and then you suck a little more and you look and it's blue because it's layers, right? It's like layers on top of layers. That's exactly how an atom is structured. It's layers, but they're not, we like to think of them as like perfectly round, like a ball inside of a ball inside of a shell, right? But really they make all kinds of crazy shapes. They're not exactly what we, yeah, they're not just, right? They're not like Russian dolls, right? But it's the ones on the outside that matter. It's the ones on the outside we're looking for. Those are called your valence electrons because they're the furthest away from the nucleus and they're the ones that can interact with things.
I watched a Food That Built America documentary on Everlasting Gobstopper. Fun fact: the nerds actually came from Everlasting,
Like the leftover bits or something.
Yep.
Oh, who knew? All right, so valence electrons may be what from one atom to another? What do you think?
Transfer.
Yeah, they can be transferred. Yep, and they can also, there's something else that can happen. They can be transferred or they can be shared. Okay, and there's 2 types of bonds. When you have a transfer, you're going to call it an ionic bond, and when you have it shared, it's going to be called a covalent bond. And we'll see a little more as we move along how that works. So these would be our valence electrons. You see how they're on the very outside shell? All of these are electrons, all these in here, electrons, electrons, electrons. But these electrons don't interact with anything because they're closer to the inside. Only these guys on the very outside are the ones that can interact with other atoms. What element is this? Do we know?
AI.
It's an L. It's hard to tell, but that's an L, A-L. Aluminum. Very good. Right. Very good. All right, now isotopes. All right, these are different isotopes of carbon. So isotopes of an element have the same atomic number, but a different mass because they have a different number of what? Anybody know?
Neutrons?
Yes, neutrons. Sup?
Pressure gauge.
I have a, yes, I have a pump that has a gauge on it. Your tire low? Do you? Like a blow up one? Do you need an umbrella? Okay, let me know what you need. All right. All right, so it got cold overnight, James. That'll do it sometimes, you know, because it decreases the pressure inside your tire gauge for his car. All right, so a different number of neutrons. So what happens over time? So if we're looking here, this is where carbon starts out, right? We just saw it a minute ago. 6 protons, 6 neutrons, 6 electrons. But carbon can change. Carbon can end up with 7 neutrons. Can also end up with 8 neutrons. And these are called isotopes, okay? So basically that means they're going to behave a little differently because now their mass is different, but the electrons that are on the outside are still the ones that can do the interacting, all right? Now, when you think about one more thing about isotopes, when we get into stuff next year, we talk about like radiocarbon dating, and we talked about it a little bit at the beginning of the year when we talked about how like rocks and fossils and things can be dated. And that's what they use is isotopes, but they use isotopes of very, very heavy elements. And that's how they figure it out. All right, so let's talk about metals for a minute. All right, chemists classify an element as a metal based on physical properties such as what? What are our properties of metals? Who can tell me? Anybody know? Yes, go for it, Carlos. Yes, hardness, shininess, malleability, and ductility. Okay. So we'll talk about what that means. That metals can show a wide range of chemical properties. Metals in a blank or blank on the periodic table. Do we know what those words are? I'll tell you. It's going to be a group or family. Have similar properties. And these family properties change gradually as you move across the table. So let's just look at the table for a minute here. All right, first and foremost, we have alkali metals. So we just put a box around them. Here, they're like this kind of peachy color. Here, they're red. Okay, these are your alkali metals. Now, these, I will tell you this, these colors, unfortunately, there is no standard. So you'll look at different periodic tables and there will be different colors. It's just kind of, I think a standard should be made, honestly. I think it would be easier for everybody to remember them if the standard was made, but we don't have one. So just know that that color means nothing except that artist liked that color. All right, so, yeah.
How come that table is different than your table?
That table is what?
That table doesn't have this category of gray colors.
Ah, okay, yeah. So it does.
Unknown chemical properties.
It does. They're just right here. They're not divided out as something different. And that's because there are multiple ways to categorize things.
Is
So
yours correct and that is wrong?
they're both correct. This one's a little more detailed, is all. So there are multiple ways to categorize things. You can say, like you'll see in a minute, there are some things that are going to fit into like one of these categories, but then also separately. And right here, you can see them separately. See these guys right here, these kind of, I don't know, brown colored ones,
Yeah.
but up there, they're not chunked out. So this was a little more detailed, but some things are more than one thing, if that makes sense. So then you've got alkali earth metals. These are these right here. Over there, they're orange, right? All right, how about rare earth metals? What color are they on our chart?
They are purple.
They are purple. Very good. Now, here's the thing to notice. You see this right here? 57 through 71.
Yeah.
This is 57 through 71. We can't fit them in that table right there because it won't work. So basically what they've done is they've taken that out and plopped it separately. But you have to imagine that if you're going numerically, that's where they fit. But the way things are, yeah, and the way things are grouped, this works very nicely because they share properties. So I'll give you another one. This big chunk in the middle, transition metals. Okay, now
That is
Yeah, see, it's blue here, but then there's a little bit of the gray mixed in, right?
The periodic tables are.
So like, for example, these can be considered transition metals, but really they have some unknown properties that just, we aren't as clear. So this is denoting them as, oh, a little different, right? All right, then we've got this chunk right here. And these are our other metals. We're just gonna call them other metals here. And if you look over here, they're further broken down, right? Like we've got mostly this blue section, and we're calling them post-transition metals over here. So sometimes they're different names for things, all right? Then we've got the non-metals are located to the right of the zigzag line. You see a little zigzag line, right? Located to the right of the zigzag line in the periodic table. And in general, the physical properties of non-metals are what to those that characterize metals? They're going to be opposite. Okay, so on the border between the metals and the non-metals are the 7 ones we call metalloids. Okay, so if you look on this chart, you can really see the metalloids, right? It's that kind of, like we said, that brown color, that weird color. And those are going to be your metalloids. And then we've got other non-metals. All right, so if you look at these other non-metals, so a lot of these are solids that are not metals. Some of these are not solids. For example, these are all gases, and then we know hydrogen's a gas, right? So there's a lot going on this table. Yeah,
Why
and
are
there's
they highlighted in red?
just so you can see that they're non-metals, like they're just different. And then your metalloids there, we have the little purple lines around them. And there they are here, they're that brown, right? Okay, now, studying atoms. Ooh. Hang on a second. Oh. I don't know. Occasionally a boat goes down the river.
I think someone's vacuuming upstairs.
Nah, might be my mom downstairs. All right, so let's look at studying atoms. Here we go. So, all things are made up of the elements. Earth, wind, and fire, and water. I'm Aristotle, and I know things. So back in Aristotle's time, the elements were earth, wind, fire, and water. Have you heard that before as being called an element? Yeah, that's like old school elements. Yeah, that kind of thing. All right, then we have ancient Greek models. So we had Democritus. This is our Democritus rat. So he believed that atoms were uniform, solid, hard, incompressible, and indestructible, and that they moved in infinite numbers through empty space until stopped. And differences in atomic shape and size determined the various properties of matter. So this is Democritus and how he's envisioning things, all right? So way back in the day. Then after, oh, he says, I shall call these, too fast, atoms, for atomos means indivisible. So already he's missing something because they are divisible, right? They have protons, neutrons, and electrons, and then there are even further smaller subatomic particles than those. Yep. But see, he is like, indivisible. Then we have Dalton. Now we're much further out in time. We're getting much closer to where we are now. There's a big gap here. So Dalton proposed the theory that all matter is made up of individual particles called atoms, which cannot be divided. So again, we're still in the cannot be divided. Yeah, similar. Yep. So atoms are like this billiard ball, he thought. So he's similar to what Democritus said, but he's saying it's all matter. He's now relating it to matter, whereas Democritus was just like, it's stuff floating everywhere. Woo. All right, then we get Thomson's model of the atom. So J.J. Thomson's experiments provided the first evidence that atoms are made of even smaller, yes, plum pudding model. Now he calls it a plum pudding model. So he says, no, atoms are more like these chocolate, let's just say chocolate chip cookies, not chocolate chip cookies, or plum pudding. Now, plum pudding is not something that most Americans have any idea what it's like. It's kind of like a fruit cake. That's a plum pudding. So sometimes we say chocolate chip cookie because that's more relatable, right? So he thinks that they've got little small particles within them, but he doesn't understand how the structure of those particles work. So then we get Rutherford. Okay. Now, Ernest Rutherford said that an atom's positive charge is concentrated in its nucleus, and that a dense positively charged mass, that the nucleus is a dense positively charged mass in the center of an atom. So was he right about that?
Yes.
Yeah, he's right about it. We're getting somewhere. right? We're getting somewhere. So he thinks they look kind of like this. And he's like, guys, atoms have a nucleus. They look more like this. It's not just like a cookie that's got a center. And then we get Bohr. So we have Niels Bohr. So Niels Bohr postulated that electrons orbit the nucleus at fixed energy levels.
The solar system.
Yeah, very similar. Yep. And that orbits further from the nucleus exist at higher energy levels. And when electrons return to a lower energy level, they emit energy in the form of light. An electron in an atom can move from one energy level to another when the atom gains or loses energy. So he's right here. He's getting somewhere. So he's like, no, y'all, Ernest, you're close. So Bohr and Rutherford were contemporaries. All right. So he says, Ernest, you're close, but electrons are found at different levels. All right. So now we have a more modern theory, and it goes like this. All right, the electron cloud model. The electron cloud model was developed in 1926 by Erwin Schrödinger and Werner Heisenberg. All right, the model is a way to help visualize the most probable position of electrons in an atom.
Quantum mechanics.
Yes, quantum mechanics, very good. The electron cloud model is currently accepted model of an atom, and it's quantum mechanical model. Is a visual model of the most likely location, because they're saying it moves. Right. So we'll come back to why I chose a kitty cat in a box here for this guy. So this is a little more like it. Okay, so we started closer to this, and this is actually what we're going to model in lab today, is something like this, because it's real easy to understand. I wonder if that's my neighbors, because they're moving and they're doing all kinds of things over there. So
I saw the neighbors when I was.
So the most stable electron configuration is one in which the electrons are in orbitals with the lowest possible energies. So we want to have the lowest possible energies. So this is electron configuration, and it's the arrangement of electrons in an atom. So basically, you see how they're not little round shells within shells? They're not everlasting gobstoppers, because really what you have is like all of these funny shapes. They call them electron clouds. And the thing with this is it's darn near impossible to model it in a way that you can like manipulate and understand. So when we're doing it in lab today, we'll do some Rutherford Bohr, right? But that's kind of what the idea was. All right, so let's look at this real quick for a second. If it will play. Come on. Here we go. I'm going to see if I can find out what the buzzing is, if y'all just watch this for 1 second.
What do an ancient Greek philosopher and a 19th century Quaker have in common with Nobel Prize winning scientists? Although they are separated over 2,400 years of history, each of them contributed to answering the eternal question, what is stuff made of? It was around 440 BCE that Democritus first proposed that everything in the world was made up of tiny particles surrounded by empty space. And he even speculated that they varied in size and shape depending on the substance they composed. He called these particles atomos, Greek for indivisible. His ideas were opposed by the more popular philosophers of his day. Aristotle, for instance, disagreed completely, stating instead that matter was made of 4 elements: earth, wind, water, and fire. And most later scientists followed suit. Atoms would remain all but forgotten until 1808, when a Quaker teacher named John Dalton sought to challenge Aristotelian theory. Whereas Democritus's atomism had been purely theoretical, Dalton showed that common substances always broke down into the same elements in the same proportions. He concluded that the various compounds were combinations of atoms of different elements, each of a particular size and mass, that could neither be created nor destroyed.
That's the
Though he received many honors for his work, as a Quaker, Dalton lived modestly until the end of his days. Atomic theory was now accepted by the scientific community, but the next major advancement would not come until nearly a century later, with the physicist J.J. Thomson's 1897 discovery of the electron. In what we might call the chocolate chip cookie model of the atom, he showed atoms as uniformly packed spheres of positive matter, filled with negatively charged electrons. Thomson won a Nobel Prize in 1906 for his electron discovery, but his model of the atom didn't stick around long. This was because he happened to have some pretty smart students, including a certain Ernest Rutherford, who would become known as the father of the nuclear age. While studying the effects of X-rays on gases, Rutherford decided to investigate atoms more closely by shooting small positively charged alpha particles at a sheet of gold foil. Under Thomson's model, the atom's thinly dispersed positive charge would not be enough to deflect the particles in any one place. The effect would have been like a bunch of tennis balls punching through a thin paper screen. But while most of the particles did pass through, some bounced right back, suggesting that the foil was more like a thick net with a very large mesh. Rutherford concluded that atoms consisted largely of empty space, with just a few electrons, while most of the mass was concentrated in the center, which he termed the nucleus. The alpha particles passed through the gaps, but bounced back from the dense, positively charged nucleus. But the atomic theory wasn't complete just yet. In 1913, another of Thomson's students by the name of Niels Bohr expanded on Rutherford's nuclear model. Drawing on earlier work by Max Planck and Albert Einstein, he stipulated that electrons orbit the nucleus at fixed energies and distances, able to jump from one level to another, but not to exist in the space between. Bohr's planetary model took center stage, but soon it too encountered some complications. Experiments have shown that rather than simply being discrete particles, electrons simultaneously behaved like waves, not being confined to a particular point in space. And in formulating his famous uncertainty principle, Werner Heisenberg showed it was impossible to determine both the exact position and speed of electrons as they moved around an atom. The idea that electrons cannot be pinpointed, but exist within a range of possible locations, gave rise to the current quantum model of the atom. A fascinating theory with a whole new set of complexities whose implications have yet to be fully grasped. Even though our understanding of atoms keeps changing, the basic fact of atoms remains. So let's celebrate the triumph of atomic theory with some fireworks. As electrons circling an atom shift between energy levels, they absorb or release energy in the form of specific wavelengths of light, resulting in all the marvelous colors we see. And we can imagine Democritus watching from somewhere, satisfied that over 2 millennia later, he turned out to have been right all along.
Or at least somewhat right. Not completely wrong. All right, so if you have a phone,
Yeah, I have one.
cool.
I have a phone, but I don't have internet.
Ah,
But,
that's okay. Well, actually, we'll go without. We'll play without the phone because I have the answers. All right, so in what year was Aristotle born? Who votes for 310 BC? Who votes for 385?
Yeah.
Who votes for 483? And the answer is going to be 384. I cannot speak. 384 BC. So there's our little dude there. All right, true or false?
Yeah, you have to find that.
No. True or false? Aristotle lived with his parents until he was 40 years old. What do we think? Who thinks it's true? Who thinks it's false? All right, so Aristotle was orphaned at the age of 13. That's sad. Definitely didn't live with his parents till he was 40. So St. Thomas Aquinas gave Aristotle which posthumous nickname? What's posthumous mean? It means after he's dead.
Oh.
So after he died, St. Thomas Aquinas gave him a nickname. Was it the man who knew everything, the philosopher, or the master? What do we think?
The master.
The man who knew everything. Oh, we got all three. So during his lifetime, Aristotle was known as the man who knew everything. But later, St. Thomas Aquinas posthumously nicknamed him the philosopher, as in the only one you'll ever need, the philosopher, right? And in the late medieval era, Dante named him the master in his masterpiece, The Divine Comedy. So Aristotle has been touted for many, many years. So, and this is what Aristotle probably looks something like this. Hopefully he didn't have dead eyes like that, because those are some scary dead eyes. But yes, that would be Aristotle. All right. Now, in what year was Democritus born? 400, 432, or 460 BC?
432.
460. All right. And True or false? Plato admired Democritus. Plato's another big old philosopher. What do we think? So Plato claimed that, sorry, Diogenes claimed that Plato disliked Democritus so much that he wished to have all of his books burned. Daggone Plato. Eee, censorship. All right, so what was the nickname given to Democritus? Anybody want to guess?
The man who knew everything.
The man who knew everything?
No, Mr. Matter.
Mr. Matter. So he was the laughing philosopher because he was often cheerful while at work. Okay.
I thought it'd be because
He loved to
people,
be,
like, laughed at.
he loved to think, and he came up with, made him happy. So Democritus, hopefully also not dead eyes like that, but he probably looks something like so. Look at his fancy curly beard.
I like how the mouse looks.
Yeah. So when did John Dalton live? So we got 1736 to 1800.
I think 1766 to 1844.
Let's see.
It's also 17.
Very good, Eunice. Eunice nailed it. All right, so here's our John Dalton. Where was he from? What do you think?
France, England.
France, England. The name like Dalton. It's going to be Canada, Germany, USA, England.
England.
England? You're right. He's an English guy.
John.
Okay, so what was his religion? Do we remember? I think they mentioned it in the video. So your options are going to be Church of England, Roman Catholic, Quaker, Latter-day Saint, or Hindu. Quaker. What do we know about Quakers?
Quakers are very strict. Susan B. Anthony was a Quaker.
Who was?
Susan B. Anthony.
Susan B. Anthony. Yeah, Quakers are very strict. They're very conservative. They're very
They don't like to like dress and put a bold clothes.
yeah, but they're also very, very peace oriented. They're peaceful people. Like they don't do war, that kind of thing. They can be a conscientious objector if you are drafted or whatever, and you're Quaker. So he was Quaker, right? Okay, where do you think he went to college?
In England.
So we got, let's see, what are our options? Are they gonna pull up? Hello. Oh, no, you get to guess. Anybody want to guess?
What is that one called in England?
There's
The very famous
Oxford, Cambridge,
one? I'm saying
Essex, Cambridge, we think. Okay, so yeah. Around 1790, John planned to attend college studying mathematics, but since he was a dissenter, so this goes back to being a Quaker, he wasn't allowed to study at English universities. John never attended college as a student. A dissenter is a member of an organization that opposed the Church of England. So Quakers do not fall under the umbrella of the Church of England. Do you know what Christian denominations fall under the Church of England today? Or it's basically just the Church of England, but the broader umbrella is Anglicanism. So in the UK, that's Church of England. In Canada, it's Canadian Church of something. In the US, it's Anglican and Episcopalian. So that's my family. But yeah, that's all church, that's all Anglicanism. So he was not Anglican, he was Quaker. So therefore, they wouldn't take him at any English college. So true or false, was he colorblind?
Yes, because why would it?
Why would we ask that otherwise? Yeah, he was, interestingly. All right. And this was John Dalton and probably this is a sketch of him. So that's probably pretty accurate. Sitting there looking very, very, I don't know, what's the word for that? Serious. Very serious. Okay, when did J.J. Thomson live? So we got,
1912 to
1856 to 1912.
all right, let's see. 1856 to 1940. All right, so he lived a good life. That's pretty long, right? Where do you think he's from?
England.
England again? What are we
UK.
thinking? Everybody's thinking England?
UK.
All right, so
Irish.
he was English again. All right, now, what do you think JJ stands for? So I got, that's John Joe, Jacob James. So our options are going to be Jeremiah Jones, Jethro Jacob, Joseph John, John Jacob, Jedediah Jeremiah, or James Joe, John Jacob, Joseph John. There you go. But he went by JJ, right? So was he knighted?
Yes. Why would we ask that question?
Why would we ask that question if he wasn't knighted? So he was. He's part of his Order of Merit is the Fellow of Royal Society. There are multiple orders of, if you're knighted, multiple orders, right? So this is his order. So how do you think he met his wife?
Conference call.
Conference call. All right, that's
They-
interesting.
Is it a multiple?
Did they have conference calls? So here are options. At a concert, on a carnival ride, at a physics lecture, saved her from drowning, or it was an arranged marriage.
At a concert.
I think it's out of physics.
Saved her from drowning. These are great. So in 1890, Thompson married Rose Elizabeth Paget at Church of St. Mary the Less Rose, who was the daughter of Sir George Edward Paget, a physician, and then Regius Professor of Physics at Cambridge, was interested in physics. So beginning in 1882, women could start to attend demonstrations and lectures at University of Cambridge. They could not be students, but they could attend lectures. So she did. And among them was Thompson's. So she met him by attending one of his lectures. So what do you think became, they had 2 children. What became of their 2 children? This is open response. Any
Oh,
guesses?
What do you want?
Do you think they were famous scientists too? Do you think they became like movie stars? So they had 2. One was awarded, this is George Paget Thompson, awarded a Nobel Prize for his work on the wave properties of the electron. And then Joan Paget Thompson, later Charnock, became an author writing children's books, nonfiction, and biographies. So both of their kids are well-known, well-established people. So there's JJ. He's got a great stash and some lovely spectacles there, looking good. Now, Ernest Rutherford. When was Rutherford alive?
88.
88 to 45.
And 1937.
71 to 37. All right. So where was he from?
From England.
There's that name, Rutherford. What are we thinking it is?
I think it's from UK.
It's England.
Think it's English?
Can I think the options? Oh, no.
New Zealand.
New Zealand.
Oh,
Which is-
nobody expected that,
which
which
is
was
a
part of the realm,
colony.
the British realm. Yep. So Rutherford, whoops, what was the question? Yeah, New Zealand. Okay, Rutherford briefly held a world record. What was it for? Was it for holding his breath underwater, the longest distance over which electromagnetic waves could be detected, highest SAT score, hot dog eating contest, or fastest transmission of digital data?
I think it's hot dog. No, I
Hot dog
think
eating.
it's the second.
So with encouragement from his mentor, J.J. Thomson, Rutherford detected radio waves at 0.5 miles or 800 meters and briefly held the world record for the distance over which electromagnetic waves could be detected. Although when he presented his results at the British Association meeting in 1896, he discovered he had been outdone by Marconi, right? Whose radio waves had sent a message across nearly 10 miles. Marconi's the guy that gets most of the historical credit for radio waves, right?
Imagine if it was the hot.
So he coined a chemistry term. Was it redox, half-life, or ionization? Half-life is right. He did. So what's the smallest thing he ever discovered?
I know.
Small, like
Mm.
small or small, like not important.
Small, like tiny small. What do we think?
Particle.
Electron.
So he discovered protons. So there you go. A subatomic particle is right. So what was the cause of his death?
Heart attack.
Do you want to guess? So
Jumping off
for
a
some time
skyscraper.
before his death, Rutherford had a small hernia. A hernia is when you have like all the muscles that surround your abdomen and your groin. Like if you get a weak spot, like it can cause your internal organs to kind of put pressure on it and push outward. So he had a tiny hernia and he neglected to have it fixed.
This girl had a hernia on a plane.
Oh gosh. So then he became violently ill, and despite an emergency operation in London, he died 4 days afterwards at Cambridge on the 19th of October, and they called it intestinal paralysis. But yeah. And there's Rutherford and how he for real looked. And let's whiz through, we only got a minute. So Niels Bohr lived in 1885 to 1962. Yeah.
Why does he have human hands but a mouse head?
Oh, he's got mouse. They're little mouse hands. They're hairy and they have nails. So he was from Denmark. Bohr is from Denmark. And he studied at University of Copenhagen. And did he work on the Manhattan Project? What's the Manhattan Project? Do we know? This is the project that was involved in building a nuclear weapon for World War II. And yes, he did. Now, this is interesting. Bohr's mother was Jewish. During the 1930s, Bohr helped refugees from Nazism, and after Denmark was occupied by the Germans, he met with Heisenberg, who had become the head of the German nuclear weapon project. In September 1943, word reached Bohr that he was about to be arrested by the Germans, so he fled to Sweden, and from there he was flown to Britain, where he joined the British Tube Alloys Nuclear Weapons Project as part of the British mission to the Manhattan Project. And that's Bohr. And then lastly, we're going to have our last two. We're going to whiz through them real quick. So Schrodinger, this is Schrodinger's, when Schrodinger lived. And he was from Austria. He was Austrian. And, whoops, sorry. Was he solely focused on atomic theory or was he a polymath? So he's a polymath. We got statistical mechanics, thermodynamics, dielectrics, color theory, electrodynamics, general relativity, cosmology, keeps going, religion, physics, ancients and oriental concepts, dude, everything. So despite his talk of philosophy and ethics, he had serious issues with philandering. He lived with his wife and his mistress. And in his later years, pursued relationships with several minors. Not good, dude. Schrodinger, not good. There he is. Kind of skeezy. The cat in the box. So Schrodinger is known. There is something called the Schrodinger's cat, and I have a little video about it, but I don't have time. You can look it up later. Schrodinger's cat is this whole idea of there's a cat in the box. And you should watch the video. It's linked in your yeah. Is the cat alive? Is the cat dead? Is the cat alive and dead at the same time? So this is Heisenberg. Okay. Well, I'll tell you. So Heisenberg, 1901 to 1976. So he died the year I was born. So fairly contemporary. And he was from Germany. Now he played the piano quite well. And do you think he fled Germany like so many other scientists when the Nazis came? So this is the interesting thing about Heisenberg. He didn't flee. He had some family friends that were acquainted. His mother's family was acquainted with Heinrich Himmler. And Heinrich Himmler was one of Hitler's close associates, right? So he never joined the Nazi party, but he basically kept a low profile because he thought it would be over with real soon. And he didn't want to rock the boat. He wanted to keep doing his work, and he knew he was protected because his family was friends with some of the Hitler people. So he just kind of shut up and did his work, but he didn't stand up for people and he didn't run. So his wife wrote a book about him after he died called The Political Life of an Apolitical Person, and said, first and foremost, he was a spontaneous person, thereafter a brilliant scientist, next a highly talented artist, and only fourth place from a sense of duty, homo politicus, meaning a political man. All right, now that's Werner Heisenberg. Now the reason there's Schrodinger's cat, which we don't have time for now, but you can watch it later. The reason I made him look like he was wanted is the TV show Breaking Bad, which was a HBO Cinemax series that I think now is available on Netflix or whatever. But Breaking Bad is about a high school chemistry teacher who has cancer and needs money and has to help his family. So he gets into manufacturing methamphetamine. Kind of crazy. He's the protagonist in the story, but he's not really a good guy, right? But he chooses an alias, and the alias he chooses is Heisenberg. So that picture, there's a famous picture, there's a sketch of Heisenberg that like the police put out in the show. So basically I asked AI to make me a sketch, but make it a rat, and it did, which was really cool. And it looks like that actor who is Bryan Cranston. So anyway, when you get a little older, probably not something for you to watch now, but it's a very, very good show. Very well done. Yes, ma'am.
I have seen a couple.
Have you? Yes, ma'am. What you got, Emma?
Oh,
Are you just stretching? All right. So let's call our crew in. All right, y'all. You ready to come in?